Hello everyone and welcome back to our class in Artificial Intelligence and Machine Learning in Finance. We are still looking and talking about the Multilayer Perceptron we fitted to our dataset of handwritten digits that we want our model to recognize and to predict. And we've seen dropout as one way of regularizing a neural network. Remember that we saw that even our very simple single layer perceptron had 204,000 parameters. The multi-layer perceptron with 3 hidden layers had close to 250,000 parameters, and they were prone to overfitting. So we need some way of regularizing those neural networks. And the second way of doing this is early stopping, which is a very simple procedure that actually decides when to stop the training of the data when overfitting starts to come in. So we now want to fit a model with early stopping. You can go back to slide 335 to see what early stopping is. I just explained it. We again rely on the previous model from the previous video, the multi-layer perceptron with 3 hidden layers. And for illustrative purposes, we reduce regularization by setting the dropout rate to 30%. Apart from this, it's the same model specification as before. So early stopping, we compile and fit the model. This will be model 4. As you can see, we compile it again using cross entropy, the same optimizer and accuracy as the metric which is used to measure the predictive performance of our model. In training with early stopping, this is where it's now different from before. It's performed via introducing a so-called callback monitoring. Callback that it's monitoring the accuracy on the validation set. So we fit our model 4 into history. This is the object based on X train, Y train, 50 epochs, batch size 64, and 20% of the data is used for the validation set. That's as before, that's the same, but now callbacks is a list. Callback, early stopping, we have to monitor the accuracy. The patience is a parameter, will be 5, and restore best weights if this is, if we have seen that actually the accuracy deteriorates, should we restore the best weights? This option is set to true. So these are the parameters. Monitor is the quantity that needs to be monitored, in this case the accuracy. Patience, the number of epochs with no improvement after which training is stopped. And restore best weights is the option whether we should restore model weights from the epoch with the best value of the monitored quantity, or if we should stop, let's say, the patience number of epochs after we've stopped. So these are the parameters, and this is the training process. If we plot history, we can see that with less dropout and lower dropout, we could have done this even without additionally using dropout for regularization. We can see that yes, the accuracy is quite high for the training and validation set. We can also see that the loss actually increases and has been increasing, let's say from epoch 5 through epoch close to 23, I guess, in the validation set, but this is where it stopped. And we've seen before that actually this would increase to this point in epoch 50 with the accuracy being just as high. So this is probably a good point. We could have also stopped maybe here. We should have used different parameters in our early stopping. So if we evaluate model 4, we can see it has 97.8% accuracy and close to 15% loss. So the classification accuracy has slightly improved compared to the previous deep model. However, to assess whether the improvement is due to early stopping, the lower dropout rate, or just happened by chance, one would have to perform further analyses. So it's not a 100% fair comparison because we've changed the dropout rate as well to exemplify this effect of early stopping. Obviously, you can try different models and different choices for the hyperparameters. Okay, so both deep models do not achieve a better performance than the shallow model with dropout. So we can see that deeper models are not better per se if we take the accuracy. And neural networks need to be carefully specified and trained, and deeper models might perform better with more training examples, with a different dropout rate, different number of neurons, layers, etc. We have a lot of ways of changing the different models. And on the following slides and in the next video, we will consider a different network architecture, that is the convolutional neural network. And this is especially suited for data, like in this example, with a grid-like structure such as the images we are going to process here.